Okay, good deal.
He's like in like the library. Like
I wouldn't try it.
I would.
I put my money on.
All right, the point is, I had the point of, I don't know. The point is, the one they gave you involved square roots of 3, so I may as well do something like that. If I do x is 1, the y, let's make the y of square root of 3 over 2. It's something, now that's in the xy plane. So if I put it on this surface, and this is what you were just talking about, if I put, here, I'm going to put this in the xy plane. There's a point in the xy plane. Here's what we're going to do. We're going to take this surface. We're going to find the level curve to this surface at, let's say, c equals 1. Okay? Then what we're going to do is drop it down to the xy plane. This will be a point on that level curve. And what we're going to do, we're going to do a couple things. We're going to find the gradient at that point. We're going to find the unit normal, the principal unit normal vector to that level curve at that point. Actually, not the principal unit normal vector, but the unit normal vector, not the principal one, because this one's going to be pointed outward. And then we're going to find the slope of the tangent line, and then we're going to find the equation of the tangent line to that level curve at that point. That's what they ask you in Weber's sign, to do these things. Yes?
So C is equal to Z, right?
Yeah, it is. But this is Weber's sign saying we're going to have Z be some constants. 0, 1, 2, and they call those C values. But this is kind of weird because C is a constant. But what are we doing? We're varying C. So, I don't know how much. I don't know.
So if you had a circle, I mean, wouldn't increasing the C make your circle smaller?
Increasing the C depends on the surface. If you have our usual paraboloid, z equals x squared plus y squared, c equals 0, you get a single point. C equals 1, you get a unit circle. C equals 2, you get a circle whose radius is the square root of 2. So the circles would increase as C increased, because C increasing meaning what? That plane that you're using to intersect the surface is lifting off the xy plane.
So if f of x and y is equal to z, and the function would, let's say if we take the function and we make it equal to x squared plus y squared,
okay,
would c be equal to r squared?
C is going to be
in terms of like a circular.
Yeah, because you'd say x squared plus y squared equals c, and that c would be the r squared. That's right.
So as c increases, the circle would increase.
Yeah, absolutely right. Absolutely right. What I've got here is not a z equals x squared plus y squared, but they use an x squared over something and a y squared. The coefficients are different, in other words. So what do we get for our level curves on this surface? Ellipse. That is correct. That's exactly what we're getting. We're getting ellipses, and that's why I'm going to do this problem. And it's a little trickier with the ellipses, so let's do that. That's exactly what we're getting. All right, so here we go. Let's take a look at this. At c equals 1. Oh, what about the whole surface? What does that surface look like? Z equals x squared over 4 plus y squared. What does that do to our paraboloid? It makes it ellipsoid in nature. It's not perfect circles. You're going to get ellipses when you intersect these things. That's our level curve, these ellipses. So we're going to have this. Our level curve is c equals 1. That's our z, like you guys were saying. X squared over 4 plus y squared. And let's draw that level curve. And I think what they do in Weber's sign, they have you pick the plot of the level curve with the tangent line and the normal line. So you have to pick the right one. So let's see what we got here. We got an ellipse. Semi-major axis is what? 1. No. 2. A squared is 4, A is 2, B squared is 1, B is 1. Okay. This is that level curve dropped down to the xy plane. Okay, we've got that ellipse. So what we're doing is taking our surface, intersecting it with a plane, 1 unit off the xy plane, 1 unit above the xy plane. It's going to intersect our surface in this ellipse. We're taking that ellipse and dropping it down to the xy plane, giving us this ellipse right here. 1 equals x squared over 4 plus y squared over 1. Now, I want to take this point, 1 square root of 3 over 2, which hopefully is on this ellipse. 1 gives us 1/4. Square root of 3 over 2. When I square it will give me 3/4. Yes, that's a point on this ellipse. It's 1. Here's our point. Square root of 3 over 2. I think that's what they were doing, Teddy, in the other problem, too. Something like that. They took a point in the xy plane, which was on the level curve when you dropped it to the xy plane. I think that's what they were doing. Now, here's what we want to do. Here's what they're asking you to do. They're asking you to find the unit normal at this point. The principal unit normal points inward. The unit normal they're looking for is the one that points outward. They want this unit normal. And then they want the equation of this tangent line to that level curve at this point. That's what they want you to do. So that's why I figured, maybe I should do it in class because this could be a little bit tricky. Okay, so let's do this. First thing, we want that unit normal. Well, the way to get a unit normal is first to get a normal. Now, there's a couple ways to get this normal. One way to get the normal is to use the gradient. After all, that's what we're doing in this section. Let's do it that way. There are other ways to get the normal vector. We could take this ellipse and change it to a vector-valued function and do the normal by doing the definition of okay. We're going to do it as a gradient. Let's do it. The gradient of this function is equal to partial with respect to x, partial with respect to y. That's how you find the gradient to a function of two variables. What's that?
Isn't that what the funny upside down delta symbol means?
Yes, that's what this funny upside down symbol, delta symbol, is called del. Okay, del f, or the gradient of f. That's what it means. It means that vector whose x component is the partial with respect to x, whose y component is partial with respect to y. Very important thing, this gradient, though. It has a lot of interesting properties, and we haven't taken advantage of all of them yet either. What we'll do tomorrow is take advantage of the fact that not only is the gradient normal to a level curve for a function of two variables, but it's also normal to a level surface of a function of three variables. Tomorrow we are going to 4 space. So this will be an interesting, yeah, 4 space. We're going to 4 space tomorrow.
I think I'm going to be sick.
Oh.
What does that mean?
David.
Are we going to do maximum theory in this unit?
Max, yes, we're going to do max and mins.
Okay.
We got a ways to go in this,
So
Jack.
when
Yeah.
you're doing the gradient of f equals to those functions, the f sub x is equal to dz over dx, or like those lowercase.
Exactly right.
Okay, I just want to.
Here, I can write it that way. Oh, I could have written, I wanted to write, oh, you said z's, oh no. All right.
That's pretty cool.
That's another way to write the same thing, without the little squiggly stuff here. Okay. All right, so the gradient will give us a vector in 2 space, normal to the level curve. Well, that's exactly what we want, and this is what WebAssign expects you to do. What's the partial of this function with respect to x?
FX.
Oh my god.
Holy moly!
Who said that?
Who said that? I think he said it. I think it came from up there.
Just gonna want Jay to take it.
Wow.
What's wrong?
Okay. No, nothing. 1/2 x, x over 2. What's the partial with respect to what?
Oh, this is the game.
Woo, man. All right. Woo.
You're horrible.
Good stuff. Good stuff. You deserve it.
It's almost like he knows how to do a derivative.
All right. All right, here we go.
Do you take Calc 1?
Ooh, wow. You're a harsh crowd, man. Harsh. All right. What we want to do is find the gradient at this particular point. So what we're going to do is substitute in this point, which is 1 square root of 3 over 2. We're going to find the gradient at this point, which will give, no, it'll give us 1/2 square root of 3. This normal vector to this level curve at that point is 1/2 square root of 3. That's what this vector is here. Okay. What would the principal? Well, that's not even. We gotta make a unit vector out of it. The other one, this one, would be the one pointing inward. That's what we would use for the principal unit normal vector. We would take the opposite of each of these.
That bottom one is what n is equal to?
Yeah, this is our n right here, but it's not yet, because we got to make it a unit vector first. We want a unit normal
So
vector.
that would just be n.
That would be a normal vector, but it's not the unit normal vector.
If
Yes,
you wanted to find the tangent vector on that point, you would just reverse those?
that's correct. Swap the two and take the opposite of either one. And that's what we're going to use and that's what we're going to use. We can do it that way. We could take derivatives. There's a lot of possibilities to find the slope of that tangent line, but that's one way. Go ahead,
It's
Lee.
always going to get you in the direction, you have to take the opposite of it to get your unit normal.
Principal unit normal.
No, to get your unit normal, the gradient's always going to have you in that direction.
All right, say it again.
When you solve for your gradient, it's always going to have you heading in the direction of the unit normal.
Okay, you got to be careful. It's going to be heading in the direction of a unit normal.
Okay.
It's going to be normal to the level curve. However, okay, it's not going to be pointing in the direction of the principal unit normal, which is always pointing inward. This one's going to be pointing outward, okay, in the opposite direction. So if that's what you mean, then
That's
you're
what I
totally
mean, it's always
correct.
gonna be pointing
Then
in
you're
the
totally
direction of
correct.
the regular unit.
Totally correct. All right, to get the unit normal out of this, and this is what course compass, this is what WebAssign is going to ask you to do. You're going to have to find the magnitude of this vector. Okay, you're going to have to find the magnitude of this gradient.
And 1 second in this?
Wait,
That's going to give us the magnitude so we can find the unit normal. This is not a unit vector right now.
wouldn't that be the gradient at a point though? No.
Yes, it is at this point.
Okay.
It is. It's going to be the square root of 1/2 squared plus square root of 3 squared, which is equal to square root of 1/4 plus 3. And that's equal to, bless you, the square root of 12 13/4. And this is very much like the WebAssign thing. It comes out, I think, square root of 13, all right, in there somewhere. Square root of 13 over 2. Okay? What does that do for us? Not a heck of a lot, except it does allow us to make a unit vector out of this normal, which is what WebAssign is going to ask you for. The unit vector in that direction. I don't know why they do, actually, but they do. So here we go. The unit vector that they're looking for, I'm going to call it n with a hat, meaning a unit vector, even though it's not our principal unit normal vector, which is pointing in the other direction, is going to be equal to 1/2 square root of 3 divided by the square root of 13 over 2, which is equal to square root of 13, the 2's cancel out there, and this one is going to be 2 square roots of, yeah, it's 1 over it, and I wanted to rationalize it, so it's going to be square root of 13 over 13, okay, good call. 2 square roots of 3 over the square root of 13 right now. Oh, I didn't want to do it this way. But that's equal to square root of 13 over 13 2 square roots of 39 over 13. Holy mackerel. Is that a unit vector, or I guess? I think.
That looks beautiful.
You think that's right? You think it's okay?
Sure. Someone plug it in.
Okay, so we can verify this. Square this guy. I'm going to just verify that I got a unit vector. When I take the magnitude of this, it's going to be the square root of square this, you get 13 over 169. And you square this, you get 4 times 39. 4 times 39 is 156 over 169. Yeah, you get 1. That's it. Okay, that's our unit vector. That's the kind of thing they want, though, right there. Okay, that's what they want. That's that normal vector, not the principal unit normal vector, which is pointing inward. This is pointing outward, and it's made into a unit vector. All right, but they also want the equation of the tangent line to the level curve at that point.
One of those negative?
What's that?
You just make one of those negative?
Yes, you do. Well, you got to swap them
Wait,
and take
so-
one negative. Yes.
So that's the normal vector, but not the principal.
Yeah, that's
Okay.
correct. Good point. And it's a unit normal vector, but not the principal unit normal vector.
Okay, all right.
And that's the one going in, or the one?
This is the one going out. That's what the gradient's going to give you. It's always going to give you the vector pointing outward. So it's the opposite of the principal unit
They're not
normal.
asking for the principal?
No, they're not. They want this
Care
one.
about principle.
They don't care about principles. That's right. We don't care about morals, principles, anything. All right. So here we go.
Wow.
Glad we got that out.
And we got that out of the way.
Never had.
Here we go. What we now want to do is find the equation of the tangent line to the level curve at that point. Okay? There's a couple ways to do this. One way to do this, to find the equation of the tangent line, we have to find the slope. Well, we could find the slope of this. After all, we have its equation, this ellipse, and we could find the derivative dy dx. Another way to do this would be to take these rather nasty coordinates for our normal vector, swap them, take the opposite of any one of them, it doesn't matter if we take this vector or that vector, and use that as the slope of that line. Now, what would the slope, you got a vector here, what's the slope equal to? The slope is equal to delta y over delta x. You put the delta y over delta x to get the slope. I'm going to do it 2 ways. We're going to do it both ways, okay? Just to illustrate this. You ready? Because I'm going to consolidate somewhat today here, all right? So you ready? Is everybody okay? Eric? I'll look at you. All right, you're right, okay. All right, let's go. First thing I'm going to do is find the slope of the tangent line by taking a look at the derivative. So here's what we're given. Y at 1 equals x squared over 4 plus y squared over 1. That's our level curve. That's our ellipse. Okay.
This is the same picture as on the.
Same picture, except better. Oh, wow, way better. No, the other one was pretty good, too. All right, never mind, they're both good. Okay, here's our point. Okay. Here's our normal vector that we just did. And we found, oh boy. Am I still on the board up there?
You're under record.
Oh, okay. Let me move it over. Okay, good. Okay. I want to find the equation of this tangent line to this level curve at that point. Right, we need the slope. The slope is the derivative, dy dx. Let's find dy dx. So this is what I'm going to do first. Let's find dy dx. Let's find the derivative. Let's use implicit differentiation. Take the derivative of 1. Take the derivative of x squared over 4. Oh, I'm too far over now. Shoot. All right. Which one? It's okay.
Wait, isn't it the partial derivative, not
Yeah,
dy dx?
Well, yeah. We go way back. Adrian and I we go way back. Way back. Plus.
It was more of a spiritual connection.
Oh.
I'm just kidding, that's weird.
Take the derivative here, you get 2y dy dx. Okay. Let's move this guy over. Let's divide by 2y. This is our derivative. The point in question is 1 square root of 3 over 2. So this tells us the slope is equal to negative 1 over 4 times the square root of 3 over 2. You get negative 1 over 2 square roots of 3. And if I'm going to rationalize that, it would be an opposite of, or negative 1 times the square root of 3 over 6. That's the slope of that line. That's using the derivative, dy dx. Well, there's another way to do that, and that's to use that tangent vector. Okay, so let's use the tangent vector as another way of finding that slope. And how do we find the tangent vector? We find the tangent vector by taking our unit normal vector, swapping the two. Okay. And then taking the opposite of one of them.
I thought it was 2 radical 39.
Oh,
It is. Swapping the two. It is. Thank you very much.
So when you took the derivative there, was that implicit differentiation you used?
Yes. Yep. And now I'm going to do hopefully arrive at the same answer by taking this, swapping these two, and take the opposite of one of them. And it doesn't really matter which one I take. If I take the opposite of the first, I'll get this one. If I take the opposite of the second, I'll get this one. And it really doesn't matter, because all I'm after is the slope of that line. Okay? So that doesn't matter. So to find the slope of that line, that tangent line, what do? You take the y over the x, okay? That's all you have to do is take the y component over the x component, which will give you the slope, okay? Delta y over delta x. So,
Is that 2 square root of 39?
yes, it is. Okay.
Wow.
Would those be minus square root over 2 and 1?
Say that again.
Would those be minus your original point of square of 1 square root over 2?
This here. So what do you want to do with this?
Do you have to do your change in y over change in x and make it so that your negative square root of 13 minus 3 is subtracted from that point?
No. All I have to do, since this vector I can place anywhere I want, and in particular, I can place it here in standard position, which is what we have when you write it in component form. It's standard position. All I need to know is that slope of that vector. That slope of that vector would be the slope of the tangent line that I'm looking for. So I don't have to subtract it from that, because I'll get the same thing.
Okay.
And hopefully this will just give me exactly what I need. That's a good call. I see what you're saying, though. Yeah. And if this doesn't work, then I'll probably have to do what you said, exactly what you said. All right, so let's see what happens here. The 13s cancel. You end up with a negative square root of 13 over 2 square roots of 39, which is not very nice. Okay? I'm going to multiply numerator and denominator by the square root of 39.
I could even separate 39 as 13 and 3. Cancel.
Oh, wow, what a excellent, who was that, Danish? Excellent idea. That is super. What he's saying is square root of 39 is the square root of 13, square root of 3. Very nice. Very nice. And now we can knock out some square roots of 13. Okay, am I okay here? Okay, very nice. And now what I want to do is rationalize this by multiplying numerator and denominator by the square root of 3. And what happens?
That's nuts.
That is. Look at that. All right. Thank you.
I have a question.
That is great. Uh-oh. Dan's going to throw a monkey wrench in this. Go ahead.
Why are we using the unit normal vector instead of using the gradient?
We could have used the gradient. The only reason I did that is because that's what WebAssign asked you to do.
Okay.
That's the only reason. That's a good point. What Dan is saying is, Burns, you bozo guy, you could have just used the gradient, which is not a unit vector, but who needs a unit? We don't need a unit vector to get the slope. You're absolutely right. But WebAssign asks you for a unit normal vector. They want you to do that for some reason. I don't know why. But so I did that. That's a good point. Okay, so now we have the slope of that line. We have a point. Let's write the equation of that tangent line. So the equation of that tangent line is in the form of y equals mx plus b. So here we go. And we know what the slope is. And we know what a point is, and that'll enable us to solve for b. The point is 1 square root of 3 over 2. So b is equal to square root of 3 over 2 plus square root of 3 over 6, which is equal to, we'll multiply by 3 and 3 here. We get 3 square roots of 3, another square root of 3. We'll get 4 square roots of 3 all over 6, which is 2 square roots of 3 over 3. That's the b. Okay. Yeah, it looks about right. So the equation of the tangent line is y equals negative square root of 3 over 6x plus 2 square roots of 3 over 3. And that's what they want for the equation of that tangent line. Wow. I know, but that's what they're asking you
Pretty
for.
hardcore WebAssign problem.
Yeah, it is. And when I saw that, I said, yeah, that's when I should do that out in class. So that's what we're doing. Okay. Okay, I'm going to, let me just mention this fourth dimensional thing. Here's the deal. Deal is this. What we have is a gradient that's normal to the level curve of a function of two variables. That property of a gradient extends to functions of three variables. Now, where do functions of three variables live? Functions of three variables live in 4 space. Functions of 2 variables live in 3 space. Functions of a single variable, y is a function of x, lives in 2 space. Functions of 2 variables in 3 space. Functions of 3 variables in 4 space. Okay? So, let's take a look at, let's use this one. We can use this as an example. Here we have a function of 2 variables. This is an ellipsoid kind of a thing, okay? You got level curves that are ellipses, okay? The problem is to find the equation of a tangent plane to this surface at a given point. And to find the equation of a tangent plane to a surface at a given point, we need 2 pieces of information. We need a normal vector. That's how we defined planes, right? Remember, we had a normal and a point. And given a normal and a point, we could write the equation of the plane. You guys recall that? We did equations of lines in space in parametric form, and we did equations of planes in space by using a normal vector and a point. Well, we're going to be given a point. What we have to do is find that normal vector. Well, if we were to make our surface a level surface to a 4th dimensional object and find the gradient of that 4th dimensional object, that gradient would be normal to its level surface, our surface. and that would be the normal vector that we need to define that tangent plane. So what we're going to do is this. We're going to say, okay, let this be z equals x squared over 4 plus y squared. And now what I'm going to do is let w equal x squared over 4 plus y squared minus z equals 0. What I'm doing here is making our surface the level surface to this fourth dimensional object w and setting it equal to 0. What is this level surface to this fourth dimensional object? It's our surface right here. This is our surface. Okay? So our surface is its level surface. Okay? Whoa. I know it's pretty shocking, this whole thing. That's a good reaction, actually. That's a really good reaction. Okay, so what's the gradient of this? Oh, geez, I'm going to do I wasn't planning to go ahead and do the whole next section, but I want to just get it started anyways. What's the gradient to w? It's partial with respect to x, partial with respect to y, partial with respect to z. Okay, that's our gradient. If we were to take our point, okay, and our point was 1 square root of 3 over 2, but bring it up to the point on the surface. So our point is 1 square root of 3 over 2. And if we plug that into our surface, we'll get 1/4 plus 3. We get 1. We get z equals 1. That's cool. Okay, that's the point on our surface. This is the gradient. Okay. What's the gradient at this point? The gradient at that point is equal to 1/2 2 times the y, square root of 3, and negative 1. Okay? From that information right there, we can write the equation of that tangent plane. So here's what we have. We've got an ellipsoid, kind of an object. Oh, wait, it's coming from the bottom up this way. And we've got a point on that, okay? We have our normal vector that we already had at the level curve, but now we're up off the xy plane. We've got our normal vector here of 1/2 square root of 3 negative 1. Okay? 1/2 on the x, square root of 3 along the y, negative 1. Okay? This is our normal vector pointing downward like this. This is our surface coming up this way. This is normal to the surface at that point. This is the gradient to that fourth dimensional object of which our surface was a level surface. That's our normal. This is our point. We want the equation of that plane. The equation of that plane to our surface at that point is this. 1/2 x minus 1 plus square root of 3 y minus square root of 3 over 2 minus z minus 1 equals 0.
Scroll back down for a second.
I lost the bottom though. Okay, that's what it is. What do? You take the components of your gradient here, or your components of our normal vector, which came from the gradient. 1/2 square root of 3 negative 1. 1/2 square root of 3 negative 1. Take the point, okay, 1 square root of 3 over 2, 1. 1 square root of 3 over 2, 1. And that's the equation of that tangent plane. And what I will do tomorrow is to bring in, I believe I have a Mathematica demo. I must have one, right? Because your lab is on tangent planes, I think.
Yeah, there's one in the lab. Yeah.
Tangent planes. So what we'll do is do this tomorrow, where we'll take a surface and do this very thing with the surface. Okay? How's that?
So what did we just do right there?
Say that again?
What did we just do?
Here's what we did.
Give it a title.
Oh, yeah, I have to give it a title when I put it on the... what Nick did is the video's on a Google Drive somewhere out there. I'll have to tell you how to get there.
So
Nick
this,
tells me how to
is
get
this
there.
next section functions of 3 variables?
No, the next section is tangent planes. In order to get the tangent planes, I need the function of 3 variables to get a whole.
So did we just enter 4 space? Like,
Yeah, we did. We just entered 4 space for a little bit. We used the 4 space for our purposes, and then we didn't need it anymore.
If you were to give it a, if you were to like verbally give it a physical representation, what would you like describe? How would you describe 4 space?
4 space, how would I describe it? It's 4 space is 3 space moved perpendicular to itself in all directions. You see, 1 space is a line. 2 space is the line moving perpendicular to itself this way. 3 space is that which moved, that plane that we just created, moving perpendicular to itself this way. That's 3 space. 4 space is that 3 space moved perpendicular to itself in all directions.
So wouldn't that just be like a bigger box?
It seems like it would, but it doesn't. Matter of fact, that's how it's represented. When you look at icosahedrons, which are force.
You mean IKEA?
Bless you.
Four space hypercubes. When you look at hypercubes, they're always represented as a cube within a cube, kind of a thing. That's how they're represented.
So it's like math and
What's
stuff.
that?
They normally have it rotating too.
And rotated too. Yeah, it's an all
Too far, do we go up
with that?
Yeah, I know. Okay.
Thanks, buddy.
See you guys tomorrow.